Yeah, I have already typed the recording.
Okay, sounds great.
Okay, so let me start. So today I'm going to present the graph structure learning by Professor Eric Shin's probability graphical models course. And the algorithm he introduced is in very early about 2008. So after introducing the algorithm he discussed, I've also introduced two recent papers, which don't have too much of the mathematical foundation, but probably will like face the modern deep learning manner. Okay, so let's start. So in all the previous lectures, we have studied a lot of the graphical models. In when studying them, we assume that we have enough domain knowledge to design the structure of our models, which means that the graph structure is given. And for example, in this case, let me have the laser. Yeah, for example, in this density estimation, like the example, we know that there are multiple clusters in the data, and we know each cluster could be represented with a Gaussian distribution. So we use Gaussian mixture model to model our data. And for the second cases, we know that the data is in the sequential manner so that we can utilize the Markov model to model our data. And in general, we can also have some knowledge described as graph to design some Markov like Markov random Markov model, a random field model, or some expert system like in Figure 1. So, however, in many cases, the graph structure or this kind of knowledge is not given, and it requires us to design the algorithm to learn the graph from the data and provide the knowledge to the model to of later on the studies. For example, in the medical domain, like this brain cells, all we can observe is that the signal from each cell, but how these cells are connected with each other is like um, hidden things that we are not given when to the model. We need to learn and infer this structure. So there are many ways to learn for this structured learning algorithm, and one line of the research is to do it in trees. And in the lecture two, actually, we have already learned such algorithm called Trolley algorithm. The basic idea is that if we assume that uh, the independence is described as tree structure, we can firstly estimate the mutual information of two nodes, and after calculating it, we just apply a maximum spanning tree algorithm to find out the optimal tree structure for this data. And in the lecture, in the trolley algorithm, it already approves like the optimality and the convergence of such algorithm, which we will not discuss too much. And all we focus more is about the general graph structure today. And also there's some like categorization by directed and undirected ones. For directed ones is similar to like causal discoveries, which we will introduce in the next lecture of the causality, which I think will be presented by Jiang Song. And our today's focus is for undirected ones, which in most cases are modeled via the Gaussian graphical models. Yeah, this is like the motivations. There are many problems that require undirected network learning. For example, the dependency between different users in the social network, or the dependency between the web pages on the internet. If we didn't observe such links, then we need to like infer such structure. Also, such problem can be even challenging when we consider the temporal graph, where the graph will be evolved for each timestamp. And how to design such algorithm for the temporal graph is a more challenging problem. Like, okay, so let's get started. So what we want to learn today is to design a machine learning algorithm that can conduct the structural learning for completely observed graphical models. So we assume that we have observed, for example, n nodes. For each node, we will have many observed signals, and based on it, we can somehow describe the distribution for like each data points. The key idea is that we turn the network inference problem as parameter estimation. So, for example, if we for original Markov random field model, which we only consider the unary and binary interactions, the probability could be written as this. This is all the unary properties, and these are all the binaries interactions. And for all of the binary connections, where we have a parameter theta 1, 2, and theta 1, 3 like this, before each of the pair of the data. So if we consider such value to be the parameters that also wants to be learned, the learning such value uh, is exactly what we want to do for the structured learning. And of course, we want to add some constraint to this theta. For example, we want it to be sparse so that not all pair of the nodes will have connections, and and many other like the later constraints. But the high-level idea is that we want to turn such problem not in the like a combinatorial problem, but in as a parameter estimation and solve it via optimization techniques. So it, as I said, if we just assume this theta is like the connection between two nodes, we are able to obtain a parameter matrix which encode the graph structure as shown in this figure. Yeah, and it creates a bridge between the parameter learning and the structured learning. Okay, so one example of the Markov random field model is a multivariate Gaussian, which is like the most simplest case. We just use this as an example to show how to conduct such structured learning. So we can easily write down the probability probability as this for each of the data. Yeah, and to make the problem simpler, because it is just a motivating example, we just assume that the mean is 0. And we can get the precision matrix, which we have already learned in lecture 2, as the inverse of the covariance matrix. And the values in the precision matrix corresponds to the weights of the singleton and the pairwise potentials in the continuous Markov random field. So therefore, Gaussian graphical models, um, it can be regarded as a pairwise Markov networks where the precision matrix actually carries the structural information of the graph. And like determines the conditional data independencies and the partial correlations. Yeah, like this. So then it seems that the structural learning can problem is converted to as to calculating this covariance precision matrix, and by definition, if the mean is 0, then the precision matrix is exactly the inverse of the covariance matrix. But in reality, if we are dealing with a super large graph, such computation is like infeasible, because the inverse normally take about like the third lifetime capacity, which is super large for a large graph. So what we desire is to directly optimize and learn the precision matrix to define such like dependency between two pairs of the nodes. So as this Qij is a value within the precision matrix, and it somehow it can be used to determine the dependency between two nodes in the Markov random field. Is everything clear right now? So from this example, I have shown that to like uh, given n nodes which have the x, if we want to estimate their mutually dependency based on the binary Markov random field, all we need to do is to estimate the precision matrix Q. Yeah, and all the later problems will be how to estimate this Q. Okay, if there's no problem, I can continue. So one thing we want to like emphasize is that there are many uh, since the Markov like the precision matrix is the inverse of the correlation matrix. So in the early research, early days, researchers just actually utilize this correct covariance matrix to determine the like interconnection between two nodes. But there are obviously these two are obviously very different. Uh, cor cor the covariance matrix actually determines the like the independence between two random variable, while the precision matrix determines the conditional independency, which actually is the foundations of the Markov random field. So by from mathematical derivation, utilizing this precision matrix is like more accurate. But if we didn't take too like if we didn't want to have the motivation of the graphical model, and we just want good enough like the network, probably we can just have a simple baselines utilizing the covariance matrix, which already like determines the like interaction between two nodes. Okay, so so far we have know that to estimate the structure of a Markov random field model, we need to estimate the precision matrix and learn it. And what we want to do is to update the like learn the value of this Q. And through learning, we also have some assumption that, for example, this Q is a sparse matrix, which means that many of the entries, for example, 1 and 6 and 4 and 5, is a zero item. We wish that this Q is sparse and many of the entries is zero. And what we want to learn is what are the values are non-zero and what are the values are zero, and about how to optimize the parameters. For example, the weights of this queue is not a focus in today's lecture of Ericson's lecture algorithm. Yeah, I have said that calculating the inverse of covariance is very time-consuming, especially for large networks. So we wish directly learn the precision matrix queue, and we need the sparsity to like force it to only have a partial entries to be one to be non-zero. Okay, so let me first introduce what is the ideal algorithm to learn this queue, and after that, we will dig into why this algorithm works and have the mathematical foundations that such algorithm is indeed learning the precision matrix. So the idea is the idea of this algorithm is super simple, so that for each of the node, for example, this node 1, we will assume that this node um, like is a combination of all the other nodes, and we want to learn to turn this problem into a linear regression problem by estimating this node's our target node's value based on all the other nodes within the graph by the value of all the other nodes within the graph. So that is as a simple linear regression problem y equals to beta x. And through learning it, we also want to add a constraint that this regression is the learned beta is sparse. So a very standard ways to do this is LASSO constraint, which is like the L1 constraint to it. I think most of us know that adding the L1 norm as constraints as a regularization can somehow approximate the beta to be sparse, which is like L0 norm. Yeah. So all we want to do is to solve the lasso regression for each of the node against all the other nodes. And after that, the beta we get, which is like how the other nodes contribute to our target node, uh, will have some items to be zero and the others to be non-zero. And we will only consider the zero or non-zero cases. And for all of the zero items, we will just assume that these two nodes will not be connected. Yeah. And to solve a lasso L1 regression problem, yeah, if we are familiar as we are familiar with the convex optimization, which we have learned quite a lot from previous lectures, we can just write down like the Lagrange multiplier by turning the constraint to the optimizers with a Lagrange term and solve this. And intuitively, why L1 regularization can force to be sparse is could be interpreted as this. Our objective in this in here is like a ellipsoid, and the constraint space is like this square, like and most of the cases, the optimal value will be achieved on this like the anchor points of this square, and for these points, many of the entries in different dimensions will be zero, and only partial of them are non-zero. Yeah, this is like the heuristic intuition, geometric intuition, why the L1 regularization can force to make the learning to be sparse. For more detail, you can go to the Lasso's deduction, and I think the paper have more like details about why this can force sparsity. And yeah, we can skip this. The algorithm is simply repeat the lasso regression for each of the nodes, and notice that i- uh, if one node, for example, node two, when we regard it as a target, it will also calculate the turns with the previous traversed nodes. For example, node one, so that we have two values, beta 1 2 and beta 2 1. And finally, the non-zerity is just a maximum of this. Yeah, this is like a very simple algorithm, which is easy to implement and easy to understand. And from the original paper, the authors have a very complex deduction about why this algorithm can under the constraint of uh, like the network density is larger than something, then with high probability the learned beta will be similar to the optimal beta star, which is like the precision matrix. But the Erskines lecture didn't follow the original proof uh, to understand this algorithm. Instead, he's still utilizing a more high-level example to show why this estimating this beta, this lasso regression, is exactly the value we want for the non-zerity of the precision matrix, which is the following. So he wants to show what is the intuition behind this graphical regression, why this works for estimating the precision matrix. Okay, so to understand this, still we can utilize in the simple cases as a multivariate Gaussian. And now we want since we want to estimate the precision matrix, which somehow determines the conditional probability of one variable to the others. So we first have some like the preliminary deduction of how to estimate this conditional probability, which is like the basic deduction for this multivariate Gaussian. So suppose we split the data to be x1 and x2, which are just upper part and the left part, so that we can split the mu and the sigma to be x1, x2, and sigma 1, 1, sigma 1, 2, sigma 1, 2, 1, and sigma 2, 2. And how to utilize all these values to write down the conditional probability of x1 given x2. So yeah, the actually didn't list it in the lecture, but this part is actually the most basic like property of the Gaussian models. So if uh, we can easily know that the px2 can be written as another Gaussian x2 given the corresponding mean and variance, which is mu2 and sigma 2, 2. And based on px1 and px2, we can also know that the conditional probability of x1 given x2 is also a Gaussian with a mean m1 given 2 as this. That's mu1 plus sigma 1, 2, sigma 2, 2 square inverse, and x2 minus mu2. And also the conditional variance could be written as a composition of the basic ones. So this shows that when we want to estimate the conditional probability of x1 given x2, we can still get another Gaussian with the mean and variance as the composition of the original mean and variance. Okay, and noted that here we want to calculate the inverse of sigma of a covariance matrix, and in the linear algebra, if we want to write down the inverse, one way to do that is to utilizing the Schur complement. I don't know its pronunciation is Schur complement, and yeah, uh, I personally learned that many times in the convex normalization courses. The basic idea is that we firstly want to turn arbitrary matrix into a diagonal matrix. For example, given the matrix M equals EFGH, we want to firstly multiply it with these two terms to transform it into a diagonal matrix where the two items is a composition of the original entries of the matrix. And when we want to calculate the inverse of it, we just need to firstly do the inverse of the diagonal matrix and multiply the other two multiplier, which can be getting as this. Yeah. Till now, we can just assume that this is just a tool for us to calculate the inverse. Okay. So based on this matrix inverse lemma and the original sigma, like the sigma matrix, now we can calculate the precision matrix. Since we all know that the precision matrix is the conditional probability of x of any two variable of q. For example, qij is pxi given xj, and based on this, we can calculate the Q matrix by the inverse of the covariance and just like put this one into here into the matrix inverse lemma. We can get this final value, and we just simplified this like a large term as Q minus 1. Yeah, and all the others are like simple terms as Q1 1 Q1 and minus Q1 transpose. Okay, so from this we can see that the precision matrix is simply in this form for the multivariate Gaussian model. So now we want to see how this is connected to the lasso, which is linear regression. So why these two are have the connection is because by plugging in the values from the previous deduction, it can be simplified as a single variate Gaussian for conditional auto-regression of the random variable. So still, let's take the mu equals to 0. This is a simple cases. So when we want to estimate xi, given all the other nodes minus x minus I, uh, we can write this term, which is how each random variable xi is conditional on all the other nodes by like uh so previously in the first pages we have already see how to write down the conditional probability of a set of variable to the remaining sets, and now we are curious about how a single node is related to all the other nodes, for example xi to all the other nodes, which is x minus I. So I copy paste the results of how one set of x1 to condition on x2 to here, and we can use these results to write down the remaining ones, how xi is given x minus I, and we don't need to pay too much attention of the values, but the conclusion is that this is still a Gaussian, and if we assume that the mu is 0, the final result can be simplified as this. So notice that in between we have the precision ones, which is sigma's inverse. You can just plug in the ones that we previously calculated, which is a q inside, and by the simplification, the final things we get is the Gaussian, which the which its value is the positive proportional to qi's value, which with the normalization. So what does it mean? It means that after this deduction on this multivariate Gaussian model, we can see that if the mu is 0, then each values, or we can know that each random variable within this graph, uh, when it is like conditioned on all the other nodes, the final distribution is the ones proportional to the q. And if the q is 0, then it means that this two value doesn't have the condition probability. And conversely, if we just estimate this problem, since this is just a Gaussian model, we just solve it by a linear regression or linear regression with L1 constraint, which is LASSO. We can get the value, the beta value, or the weights of the in here. And if this weight is 0, it means that the corresponding q is 0. Yeah. So as I said, from the previous deduction, we know that each node within this graph condition on all the other nodes is a simple Gaussian, where the weights is proportional to the corresponding precision matrix. So we can write the following condition auto-regression function as q as this xi equals to beta I against the others, and do it autoregressively to from 1 to n. And after we estimate the each beta, if the one entry of the beta is 0, then it means that we know that the corresponding q is 0. Yeah, so obviously this deduction is not very rigorous because we have some simplification, like we only consider the multivariate Gaussian, and also we previously we assumed that mu is 0, but the overall idea is that in this graphical model, if we just consider each node with the connection to all the other nodes, then the interaction can be regarded as a linear regression problem. So far it's clear. Yeah, so right now I have introduced the high-level intuition of why this simple algorithm works. This algorithm is called the Mancherson-Bollerman algorithm, which is MB algorithm. Basic idea is that for each of the x, it will solve a corresponding lasso and just take the non-zero ones to be the ones that determines the graph structure to be non-zero. And obviously, there are many more complex algorithms after that. For example, this one is what I personally and also Shichang frequently used for doing the discrete assignment. the basic idea is still we want to calculate a sparse precision matrix. Um, and suppose we already get the simple covariance matrix S by solving this optimization problem, which is the line determinant of Q minus the trace of SQ with a regularization, L1 regularization of Q. We can get a good approximation of the precision matrix Q, given the covariance matrix S. Still, as I said, the Q is by its nature is we just want to get the inverse of the S, but since it is hard to compute, we can solve it by such like optimization problem. Yeah, I will not. This lecture didn't discuss the too much details of this regarding to why this objective is the ones to get the optimal Q. We can refer to the original paper. Okay, and the previous algorithm can be easily extended to the cases where the nodes feature are discrete by just turning the distribution a probability of xk given all the other nodes x not k to be the logistic regression instead of a Gaussian. So in this case, all the other remainings are the procedure are the same. Yeah, so far I have finished the algorithm introduction of this MBA algorithm. Is there any question for this? Okay. Then Eric Shin's group extended these algorithms to the temporal graph in 2008 and 2009. So in this lecture, he also introduced this such extension of how it can be adapted to evolving social networks. So the basic idea is still we want to estimate the graph structure for each timestamp. But the high level idea is that we don't want to do it identically. We don't want for each timestamp to estimate a different structure. We want to see how the structure of for different timestamp they must have some correlation. For example, the structure for each two timestamp to uh, continuous timestamp is similar to each other. So based on this intuition, they add some regularization for this and solve the questions. And they have two algorithms, which corresponding to two papers. The first one's idea is that when they want to estimate like the probability for each timestamp, for example, timestamp t, since this timestamp t obviously have the correlation with these consequent timestamps. So one idea is that they can they do it by a weighted sampling. For example, when they get a probability for timestamp t, we also have a probability to be to sample like of mutual probability for t minus 1 or t minus 2 with weight wx wt. And this WT can be modeled via a simple kernel value by the feature value in timestamp t and target timestamp t star. Yeah, by doing so, they involve the correlation between two consequent timestamps to be somehow similar, because when you calculate the like the density of a single of timestamp t, it will also take utilizing the smooth value of the consequent timestamps, so that they will by inherently be similar to each other. Yeah. In that paper, they also have some proof about the dependency, the smoothness. Yeah, but this lecture didn't discuss too much about this. There's also another algorithm that can add a more explicit constraint, which is that for each of the timestamp, they can learn a different matrix, which is determined by theta. And instead, in this case, they didn't add the constraint as the similar dependency constraint with two similar timestamp as via sampling. The, but more naturally, they can just add it as some regularization term that minimize the distance between two consequent structure. Yeah, and all the other things are exactly similar. This part is exactly similar as the MB algorithm. They just simply add like the regularization to penalize the distance of two consequent like a structure. Yeah, and here are some of the visualization they learned from this dynamic structured learning algorithm. And one example is the CNATE network. They use the data that consists of voting records of like 542 billions of the 100 senators, where each vote is a binary outcome, and they want to see how like the votes for one senate like evolved to the time. And this is a things they learned. For example, given this is like an overall picture they learned. As you can see, as time evolved, the structure will be modified for a little bit, but most but the high level structure will be will be close or will be similar for two consequent timestamp. For example, there are two parties, and most of the structures remains as time evolves, but there are some minor changes evolved by the time. Yeah, here are still an example. Also, such algorithm can be utilized for the biological domain. This is like the breast cancer cell, how and tries to learn how it develops over different stages, such that scientists can observe different structures over time. And the goal is to determine if the cell is normal given its structure. So, uh, so this is not a temporal graph, but still they have different stages. So similar to the previous algorithm, actions group tries to penalize the total variation of the graphs adjacent to different stages, and this is like the like evolving like the graph structure they learned. Yeah. So the idea is to somehow penalize the difference between two adjacent cell types. Okay, so such structured learning's problem can also be extended to more complex graph data like the directed graphs, which we will learn in the next lecture, and also for some missing data and multi-attribute data. All of this research are conducted before the deep learning area. So the um, most of successful approaches are the graphical models. Yeah, this is all about algorithms lecture. Do you still have any questions? So to sum up, we have discussed for the graphical Gaussian model, uh, we, we we proved that the precision matrix encode is structure. It is not proof. It is like our assumption, and our goal is to estimate this precision matrix. However, it is in most of the cases not estimatable because uh, the dimension of nodes is much larger than the data samples, not only because of the time complexity, but also because like the accuracy of doing so is very low. So it's not in many cases not estimable. So now, one possible manner to solve this problem is by like the doing auto-regressive lasso, and also it can be regarded as neighborhood selection. So for each node, you just assume that it is connected to all the other nodes and adopt a lasso regression to it to find out all those links that have 0 items and just remove all these links from the global structures. And such algorithm can also be adopted to the time varying Markov networks, which we can learn different networks for different timestamps. And for like temporal graph, we can do the kernel reweighting estimation, or we can explicitly like penalize the total variation across the consequent times. Yeah, this is all about the methods introduced by Eric Jing. And of course, such like the algorithms have because it is based on the Markov network. After a lot of graphical networks, after we learn it, we can have some good mathematical interpretation of the learned ways as a dependence the dependency. But somehow the simple algorithm might not be work for more complex like data, where the input data cannot be modeled as a distribution. Most of the cases we just have a single vector, and although we can still calculate as a similarity of this, but that's strategy obviously will not be the optimal ones for good graph structure data. So later on, I will also discuss the two papers recently about how to learn discrete structures, especially for for graph neural networks. This is like a paper 2 years ago, ICML 2019, about learning the discrete structure for graph neural networks. The basic idea is still if we want to adopt the GN to a data set, we need the intermediate graph structure of the data. But in many cases, such graph is unknown. So we want to infer it in the middle. So this group these two persons are the ones are many familiar with in the auto ML strategies. So their strategy by learning this discrete structure is also by solving like the inner optimization, outer optimization. This is like their overall problem setting that they are interested in learning a GM model given a feature and the adjacent matrix, but the adjacent matrix is also the parameter that wants to learn. So if the A is given, then they can just train the weights for the GM through this loss. But if A is unknown, one way to optimize this is similar to the like the meta update in the AutoML setting that after they get a GN parameter theta, they can optimize the A adjacent matrix weights by maximizing still minimizing the loss on the validation sets. In this case, it can get it can somehow regard this A as a hyperparameter to and use another validation set to update this A. And still there are some challenging because obviously there are some challenges because the A is a discrete uh, like the vector random variables because the adjacent matrix is discrete, and in GCN setting we only consider 0 and 1, so that they model the adjacency matrix as a Bernoulli distribution and parameterized by a theta by learnable continuous parameter theta. In that case, they can somehow sample A based on this learnable theta, and through the update of the on the validation set, which is the outer update, they only need to update the probability parameters. Yeah, this is like the overall framework. Given the several data points and the generator theta, this is a graph generator theta, which to denote how each two adjacent nodes are connected, and the GCM parameter W, so that they can do it in the as a bi-level optimization steps. So firstly, they sample the graph by from this p theta, and then compute the gradients of the Gaussian parameters. After that, they can compute the update the graph generator theta by minimizing over the validation sets. Yeah, this is like the overall framework. Very simple, and you can regard it as just adoption of the hyperparameter AutoML's algorithm to this structural learning problem. And also, there is one paper in 2020 about structural learning for more robust GN. Their motivation is that since the many graphs are noisy, especially under the attacked graph. After attack, probably the graph structure will be modified and some of the very unnatural links will be added. So what if whether they can design an algorithm that can like make the input graph more real and remove all those unnatural links. For example, if we add a very unnatural link by attack model, whether we can just assign a very low weight to it so that the final graph is still close to the optimal or the ground truth ones. This is like their overall setting, overall assumptions. And to do so, they listed several graph properties they want to like maintain. For example, it should be low rank, it should be sparse, and the features linked by two oh, the linked two nodes should their feature spaces should be similar. In that case, they design such algorithms. So similar to the previous ones, they want no, not similar, unsimilar to the previous one. They want to update the GM parameters and the graph structure somehow simultaneously. Yeah, and for example, firstly they update the GM parameters, and then based on this, they update the graph structure by adding the constraint of low rank sparsity and the feature smooth, and after that they will do this turn again. So this is the like the loss function for low rank and sparsity. So the basic idea is that given the original graph and the final graph, firstly, obviously, these two shouldn't be too far away. The learned as shouldn't be too far away from the original graph. And then they added the alpha S1 to it. So this part is very similar to what we learned from Eric Xin's lecture of the like how we can estimate the precision matrix given the original like a covariance matrix. Somehow similar. Um, yeah, and yeah this turn is to somehow encourage the low rank because they don't want the entries to be too large, like the sum of the column or the row to be too large. And also they wish the learned metric can have the feature smooth property so that two adjacent like the features connected by the graph is not so it is close to each other so that they can write the loss term like this, which means that if the Sij is high, which means that two nodes are connected, are have more ways to be connected, then their feature should be similar. Otherwise, the loss term will be very high. So by putting these two graph learning laws with the overall GN laws together, they can update both the GN parameters while learning the more accurate graph. And
so Daniel, I have a question here. So for the rank, low rank constraint, do we need to specify how many, what should be the rank for the S?
In their deduction, they just utilizing this. If I understand correctly, is the like the infinite of the S, which is like the sum of all the rows and the columns, the maximum sum of column and row as a rank. It is my understanding. Yeah.
So need to pre-specify.
Oh no. I'm wrong. This is a spectral node. So this is a rank of the S. by their.
But do we need to like specify that this S has to in the space with some certain rank? For example, rank 1, rank 2. Do we need to specify that?
The Saints didn't regularize this. They just estimate this rank. This is my understanding. So they will calculate the rank of S. So the S is should be the like the a fully learnable matrix, and for given matrix, obviously we can calculate this rank. And they didn't specify their rank to be D. Otherwise, although I think it is doable because in a convex optimization, such constraint can also be converted as a Lagrangian term. But this paper seems didn't do things like this.
I see.
So probably it's because they didn't know exactly what should be the rank for a given data set. They just penalize it to not be too large.
Okay, makes sense. And the second question is like they wanted to put all those different laws together. Then in terms of the optimization part, so it seems to me like for the GN, right? So we need to require the S. So is that the alternative optimization?
Yeah. They do it alternatively, but the laws will be aggregated together.
Okay, great.
Yeah. So it's somehow so this one is not alternatively. It's like doing this for a long time, and after we get the converge to a GC and it updates this theta. So this is what people do for AutoML. For this one, I think even they do iteratively. It's like iterative in a batch, so it's more smooth. Yeah. And still to handle the discrete nature of the S, they adopt the so-called incremental proximal descent. Yeah, there are lots of ways to do that, but this paper just utilizes this approach to force the S to be somehow sparse. Okay, obviously such algorithm can beat the other like the graph adversarial like the defense algorithms, but that is not too surprising. But I think this plot is somehow interesting. This plot is like after adding some adversarial edges by the attack model, whether because they learn this S to all of the possible edges. So they want to plot the values of the edges that are attacked or the edges of the original graph. As you can see, for both data sets, the values of the original address, which is normal address, are like significantly higher than the adversarial address. So it means that they can by these three assumptions, they can indeed find out those edges that are not very natural. For example, after we add some edge, maybe it will connect it to some to two nodes that are very different with each other, or it will like break the low rank property. So by adding this by adding these three constraints, they can somehow filter out those adversarial edges. So overall, I think structured learning is still a very hard problem to tackle. And there's although there's some recent works trying to get good, better graph, intermediate graph structures, there's still no consensus. What is the best way to do that? So all the three papers I discussed today transform this the adjacency matrix, which is the graph structure, as the parameters so that we can directly optimize this by some objective. There are also many works that do it in the discrete space, for example, graph generation, synthesis, and like parsing. All these algorithms are doing more like a discrete space. So, for example, given a partial graph, how to expand the next graph as a like the Bernoulli distribution. So, yeah. So, but till now, graph generation is still a very hard problem, and for example, like the for point cloud and like the biometrical graph, or like previously, Junheng have introduced the AlphaFold, and for AlphaFold, how to estimate the intermediate structure, all this kind of problem is still very hard, and I think worth like spending more time on that. So that's all for this part of the lecture. So any other questions?
Is that all for today?
Yeah, that's all for the structured learning part. So actually, in my schedule, I also have a text generation part, but I look at the slides of their lecture. They just introduced the like Hu Zhiting's work on style transfer, and which also has already been presented by like Patricia before. Uh, so I assume that the structured learning should take 2 hours, so I just skip that part. Uh,
Okay, sure. Yeah, we can keep this short. I think the structured learning definitely is very interesting.
yeah. So this lecture only covers the method which is very old, but probably we can think about how to combine these graphical models methods in the old days with recent like the GM manners.
Right. I think right now we actually in a couple of applications, we face the issue like how you can generate a graph, including, for example, like in material science, right? So we really need to decide what would be the sparse graph under that set of atoms, or like in point cloud, we also face this issue. Yeah.
Yeah.
But by the way, the technology in the later part has nothing to do with graphic model.
Yeah. These two papers are not relevant to graphical models. So still currently there's not too much papers in the graph structure learning like the domain. So there's not too much works that involve the graphical models to handle it. Uh, there's a few papers by like Tangent's group that tries to, for example, learn the intermediate chain rules that they involve the EM algorithms, which can somehow be considered as they have the probability modeling. But that is not still not a graph structure. They just like infer the chain for two nodes. Yeah, so there's still a lot of space to involve the graphical models modeling into how to get a more interpretable structures.
Mhm. Okay, so any other questions from audience? Okay, so if no, probably we can end earlier today. Thank you,
Okay.
Ziniu. So afterwards, can you send me the video so then I can post on YouTube?
Yeah. I will send it to you via the email.
Okay, great.
Thank you.
Thank you. Bye.
Thank you. Bye.